Now, the last activity we have for this workshop is a demo. Sorry, we'll have a demo on cloud computing for Earth observation. In this case, using Google Earth Engine. So I'll be sharing my screen now. Can you confirm you see my screen?
Yes, we can see it.
Thank you. So I'll be showing you in a very summarized way how or what Google Earth Engine is and how you can use it to access multiple data sets and conduct your analysis. Now, this is just a very, very summarized demonstration, and there's actually a tutorial, a much more extensive tutorial coming soon. It's being prepared, and it will be made available. So if you're registered for the working group, you will receive the link to this tutorial I'm mentioning that will be available in the next month or so. So Google Earth Engine and cloud computing. Now, we've heard about the Sentinel-2 satellites several times throughout this workshop, and they're part of the Copernicus program. And the Sentinel-2 satellites generate about 1.6 terabytes of data per orbit. So this is a massive amount of information, and it's definitely something that most users will never be able to use or to process and analyze using their local machines, their local resources. So we need to ask ourselves if even if we would like to continue using our local infrastructure, can we really do that? Is that realistic in an age where Earth observation data is becoming so available and so common for multiple constellations? Even Sentinel-2, we have 2 different satellites in that mission contributing with data, collecting data on a global scale every single day. So how can we keep up with this volume of data that is available for research and applications? So cloud computing seems to be the logic answer. And cloud computing, if you're not familiar with the term, refers to the delivering of computing services, including storage of files, data, processing power, and also the development and deployment of applications over the internet. So if you want to develop a model, for instance, to estimate precipitation or to determine land cover, you can use cloud computing to do all that without having to download the data to your computer, run the models, and visualize the results in your computer. You can use the cloud, and there are multiple cloud services, as we're going to see. And I'm not recommending or endorsing any particular service. I'm just showing you one example of one service that you can use to do this. Now, there are several advantages to cloud computing. One advantage is the scalability. You can change the resources and scale up or down your resources as you go. So if you need more resources because you need to use more data, then you can scale your solution using more resources made available by the service that you're employing. Accessibility. Accessibility is very important. You can access the data wherever you have or whenever you have connectivity. Of course, that connectivity is very important because in most cases, you cannot run your analysis unless you're connected to the internet. So that may raise some issues, as we're going to see in just a couple of minutes. Cost efficiency. You pay as you go. So if you need more resources, if you scale the resources you're using, you may pay more. But if you don't need all those resources, you can scale down and pay less. Of course, that cost can be an issue, as we're also going to see. Collaboration is also simplified when you're using cloud computing. You can easily share your code, can easily share your results. You can even generate public apps to disseminate the information that you're producing. So for Earth observation, there are indeed several very objective advantages, including the faster computation. You can do the same amount of work in a much smaller amount of time. So it's much easier also to conduct the research. You can accelerate your research, can accelerate the development of solutions because you can do it much faster. And it's also easier to store all the data you need to use. You can also access advanced tools like machine learning and deep learning models that sometimes may not be as easy to use using kind of conventional development environments, especially if you're not a computer scientist and you need to install multiple dependencies and multiple libraries, and they all need to be compatible. It may be a very significant issue, and it's something we come across very often when working with users, the challenges of using those advanced tools. And using cloud computing environments, those problems can be mitigated. Finally, you can also integrate multiple data sets in a very easy way. Usually, cloud computing services like Earth Engine or Amazon's AWS will provide a catalog of data, a catalog that sometimes is even enhanced or expanded by the community. And all those data sets are interoperable. So you can integrate all that information and use it in your project, in your solution, in a very easy and very seamless way. So there are several advantages to using cloud computing. There are multiple platforms, as I was saying. You have, for instance, Google Earth Engine. It's very popular for research. A lot of users in academia resort to Earth Engine. Also, a lot of nonprofits use Earth Engine. Then you have AWS, very popular, including for industry applications. A lot of companies, including startups, do use AWS. And then you have many other providers, including the DIAS platforms of Europe, including Creo DIAS, which provide very seamless access to, for instance, Copernicus data, third-party mission data, but also products that are developed by European companies, for instance, and are made available through a marketplace where you can buy the data, integrate it into your analysis, and do all that in a very easy way. Then you also have, or you can also access solutions based on AI and even large language models, but this is slightly different from what we're addressing today. But I'd like to still mention a lot of emerging solutions that use AI and combine both the Earth observation and other data sets and provide analysis in a very easy way. And you can use those services to, for instance, obtain critical information on certain variables to support your activities. So that's something that is emerging. It's starting to become more common and will probably grow exponentially in the next few years. So something to keep an eye on. So you can choose from multiple services. Today, we're going to use Earth Engine. As Zhonglu and Sudhir and others mentioned, agencies like NASA, NOAA, ESA are also moving the archives into the cloud. There are several cloud platforms and solutions to host data from these large agencies. The solutions are different from agency to agency. The methodologies they're adopting or the solutions they're finding to make the data available still free, but taking advantage of those enhanced solutions that are made available or made possible by cloud computing services. are also different from agency to agency. And I do think that in the next few years, we're going to see a lot of a very fast evolution and a lot of trial and error. So as we move towards the cloud, as more and more users adopt it, I think these services will evolve very rapidly as well. And we'll have to learn to cope with those, with that very dynamic environment and the changes that are almost inevitable. So all this is very good. We're moving in the right direction, but some caution is definitely needed. So the cost of cloud-based services may be an issue. Cross-border access limitations may apply. There are some cloud services that may be available in one country or one region that may not be available in a different region. So that's something that's very important to take into account when you're signing up to a cloud service, and also when an agency is moving towards the cloud. The dependence on external providers, including private companies, is something that will introduce some changes in how we deal with data, how we store data, how we access data. And when I say we, I say we as the society. And of course, there is some lack of control and privacy concerns that will also have to be addressed, regulated, and the users need to be aware of. The skill and technical gaps are also a problem. So again, we were talking about coding earlier. Most of these platforms require users to know some form of coding, or they will not be able to use it, the services that are made available through those cloud computing platforms. Even Earth Engine, you need to know JavaScript or Python. If you don't, then you will not be able to use this cloud computing service. So there will have to be some work towards increasing coding and programming literacy to make sure that we are opening up the archives and making data more available and not less available. So if we want to mainstream Earth observation, we'll have to make sure we understand how to make the data available through the cloud, but without excluding people. So the transition may indeed exacerbate exclusion, especially of underserved communities, if we do not take into account some of the skill gaps that are still persistent. So Google Earth Engine provides a very vast catalog of interoperable data. So you can use all the data within Earth Engine in your solution. Of course, you need to be careful about how you do it, but technically you can do it. It's free for research. If you want to develop commercial applications, you can, but you need to consult with Google and acquire the necessary licenses. And of course, you have very powerful computing capabilities and many integrated tools, including AI tools within Earth Engine. You need to use JavaScript if you want to use the code editor, or Python if you want to use the API. The API is becoming more and more powerful. I think more and more people are moving to the API. I think it's a very good solution, but the code editor, as we're going to see, is still the default for many users. You can share and collaborate. It's very easy to develop a public app, or even to develop a Google Colab, which is a Jupyter notebook, which you can use to share your data, share your analysis, and make it available within your team or to others. There is also a very large community of users sharing data, sharing tutorials, sharing tips on how to use Earth Engine, and answering questions of fellow developers every time they run into a problem. So it's a very dynamic community, very interesting, and I strongly recommend you, if you want to use Earth Engine, then do sign up to the different forums and communities that are designed to help people like you. We use Earth Engine extensively in our research team, both for prototyping, the development of certain products, the development of public apps. And one of the reasons why it's because it's just so easy to integrate different data sets and even create our own data sets. Data from Landsat, Sentinel, iMerge, all of that is available through Earth Engine. You should be careful because the data may not be exactly the same as it is, for instance, on a NASA portal or an ESA portal. There might be some changes. The data may be repackaged, but it's there. So today I'm going to show you a very quick example of how to access data from iMerge. And I'll be showing an example from a flooding event in the Pacific Northwest, so the border between the US, the state of Washington, and Canada. This event took place in November of 2021, was caused by an atmospheric river. Soils were already saturated, and so the flooding became very extensive in this region. We'll be using precipitation data from iMerge. We're going to use river basins, the polygons of river basins that is also available through Earth Engine, Sentinel-2 optical imagery for flood analysis, and SRTM topography data. Of course, that I'm just going to show you the code. I'm not going to walk you through the code, but the script will be made available later. We're going to send it to you by email on one of the post-workshop emails. Again, this is a very simple example because with Earth Engine, you would be able to do something a lot more in-depth. Your analysis could be expanded, but again, a more extensive tutorial is coming soon. So I'm going to switch to Earth Engine, to the actual platform. And okay. And so I assume you are now able to see my browser. Okay.
Yes, we can.
Thank you. So this is the code editor of Earth Engine. You have essentially 4 windows. You have the map window where the maps and the data will be displayed. You have the scripts and docs and assets window. You can access, for instance, the different scripts you create, etc. The central window is where you can actually write your code. You can use comments, and you can also write code lines to conduct your analysis. And finally, you have the console where certain results will be printed. So if you give a print order or a print command, it will show up in the console. You also have the inspector that you can use to, for instance, query the satellite imagery and retrieve the pixel value. So the location of the event I'm looking at is in the Pacific Northwest, so in the area of Vancouver. What we're going to do is we're going to first retrieve the location of river basins using the Hydrosheds database. And this is very easy because Earth Engine already includes all this data that I'm going to show you in its catalog. So all you need to do is to create a variable and call the specific data set that you want. Each data set has a specific ID, and this ID is then used to call the data and store it in a variable, in this case, the variable basins. Then you can use this layer, this variable, and add it to your map, and that's what I'm doing here with the variable basins with a certain color. It's going to be represented or depicted in a blue color and with a tag that will say global watersheds. Okay. So this is the first thing we're going to do, or that the code is going to do. And the next step will be to select the river basin of a river basin called Fraser, and it is identified with a very specific ID code. In this case, the HIBUS ID has a specific number. You have to know the number, but you could use even the inspector to query the different river basins and check the number of the river basin, the specific river basin you're interested in retrieving. And then we're going to add just that specific river basin in a different color and with a different tag. So all we need to do is actually write these lines of code and then run. When we run the code, and a few other things are showing because I also have other code there in my script window, but you can see the different river basins. They're available in the entire world, so you can see in the US, in Europe, Africa, all the different river basins, and then the specific river basin, the Fraser river basin, being shown here in red. So very easy, as you can see, just 4 lines of code, and you already have something that you can use. Now, if you look at this area here, I have a point. Now, points, polygons, and lines can be drawn using these commands here. So you have the points, lines, and polygons. All you have to do is click and then insert the point wherever you want in the map. They are very useful because they can be used, for instance, to retrieve data and build plots for certain areas. Now, the next thing I'm going to do is to show you how to load the iMerge data. iMerge data is available on Earth Engine on version 6. I assume that soon we'll have version 7 available as well, as soon as it's available from NASA on all the different runs. But for now, we're going to use version 6. So with these 3 lines of code, I'm actually loading the iMerge version 6 30-minute product. To do that, I use the ID, the unique ID of the iMerge product, and then I'm going to filter the date range that is of interest to my analysis. So it's the start date and the end date. Finally, I'm going to select the product or the layer that I'm interested in. Another thing that's very important to pay attention to is that sometimes the names in Earth Engine may not be exactly the same as the layer names in the original product. So you should be careful, and you should read the documentation, both the original documentation and the Earth Engine documentation, to make sure that you're using the right product. Okay. In this case, we're using precipitation cowl as the product to be displayed. Next, we're going to set the color gradient from the lower values to the highest values, ranging from 0 to 300, in this case, millimeters per hour. And this is done in a very easy way, again, with a few lines of code. You have the different colors represented here. So lower values in this color, higher values in this color, and then you store the information about this palette or this color gradient using a specific variable. Again, I'm showing you a lot of things, but the objective here is just to show you what you can do potentially with Earth Engine. Now, what we want to do is now add the precipitation sum. So we're going to sum the precipitation values for the entire period of analysis. And we're going to divide by 2 because we're talking about half-hourly measurements, but that are actually represented in millimeters per hour. So we need to do that. And then we're going to add the resulting variable. So this precipitation sum with the raster, with the sum for each pixel in the world, because we're not even clipping the product to a certain area. And we're going to add this information to the map. So if we do that, we can click run. Again, I'm going to delete or deselect some of the things that we'll see later, but here you go. You can see the iMerge product being calculated, or the precipitation sum using the iMerge product being calculated for basically the entire globe for several days using 30-minute intervals to generate this sum. Now you can see clearly the path the atmospheric river took, and then the very high precipitation areas around Vancouver. So if you had to do this using conventional methods, you'd have to download all the 30-minute files, load them into Python or maybe image analysis software, and sum them individually, so one by one. This would probably take hours, and it could be reduced if you had some kind of automation script, but still a very, very complex and time-consuming process. With Earth Engine or other cloud computing services, all you need is a few lines of code, and in seconds, you can calculate the precipitation accumulation for several days or more than days in a very easy, very seamless way. Now, we can continue the work and even clip this analysis, this layer, this raster to a specific area. And I'm using the Fraser River Basin to clip the iMerge precipitation sum file. And what I do, or what I have to do, is basically to add one line of code where I clip using the Fraser basin, the polygon. I clip using that spatial extent the file contained in the variable precipitation sum. So this file I can see here in the map will be clipped, and the result will be this. So I will see the precipitation values for the temporal range that I selected only within the river basin I selected. Now, I can also calculate the values using what's called a region reducer. They call it like this on Earth Engine. And you can calculate, for instance, the mean within the Fraser geometry, so the polygon that I see here, and I can print the result, which will show up in the console, and that's the precipitation cal value that I see here. So over the period in analysis, using I calculated the precipitation value within the river basin using this very simple code, and the result is printed in the console. So that's what you see here, 141 millimeters during that interval that I showed you earlier. So if we want to create a chart, the code is a bit more complex. You have more options. I'm not going to explain all the options again. There will be a tutorial. We're going to talk about this. So this is just a preview or a teaser of what you can expect in the full tutorial. But basically what we're doing is we're going to create a chart, and we're going to use that point that I mentioned that was created using this icons, this tools I have here on the map display. And I'm going to calculate the mean, the precipitation value, and display it on a chart. So when I run the code, what I get is this chart here, where I can see the precipitation values, the 30-minute precipitation values retrieved from iMerge for the location of the point where I inserted the point. Of course, I can edit the location of the point. I could add more points. I can do a lot of things. I can even load shaped files and use shaped files, for instance, with the location of precipitation gauges if I want to do comparisons or validation work. This charts can be exported, and the data can be exported in CSV format. So if you want to run an analysis on your favorite statistical software, you can do so. So it's very easy, it's very intuitive, and a very good thing about this is, even code that seems longer and more complicated, you can reuse it. It's very easy to reuse the code. Once you have the code figured out, it's very easy to apply it to other situations and develop other solutions and analysis. So this is what you need to get the iMerge data, display it, make some analysis, simple analysis, but still retrieve the data and perform some visualizations and analysis on the data. You can also add other data sets. And just to wrap this up, and we're going to add data from Sentinel-2, because we want to see if the precipitation did generate flooding, or if we can see the flooding using satellite imagery. Probably Sentinel-1, because it's a SAR sensor, would be better to detect surface water, but we're going to use Sentinel-2 because it's just more intuitive and easier for this example. So again, we're going to use the unique ID of each data set, in this case, the Copernicus Sentinel-2 surface reflectance product available on Earth Engine. And we're going to select a few bands. So these are the 10-meter spatial resolution bands. So band 2, 3, 4, and 8. And we're going to filter a date within the range that is of interest to us. So we're going to find the images that are available for this period. Then we're going to calculate the median. But in this case, this is really not important because we know we have one image available for this very small temporal range. We're going to also set the visualization parameters. So we want band 4, 3, and 2 to be displayed in order to create what we call a true color image. And we're going to add the Sentinel-2 image to the map. So if we do that, we can actually see that there are several Sentinel-2 images being collected during this period. And one of them is actually showing us the Vancouver area. And soon we'll be able to see the flooded areas, or at least where river flow is very significant. So you can see it here, very pronounced, very large coastal plumes, and the water coming from inland, caused by the very high precipitation that was measured in this area following that atmospheric river. So as you can see, with only a few, not even 100 lines of code, and this could be compressed because I have a lot of comments and space between the lines, with maybe 50 or less lines of code, you can have river basins, you can load iMerge, you can create new data from iMerge, so new temporal aggregations, you can clip the data, you can load Sentinel data to see where's flooded and where's not, you can create charts. So you can do a lot of things using very simple code that's easy to learn And one of the speakers was mentioning, Sudhir was mentioning, that you can even use some of the large language models like ChatGPT, for instance, to help you learn how to code, or at least learn how to troubleshoot and debug some of the code, especially if you're starting. It may be a very helpful resource for new coders. So this is a very simple example, again, just on how you can use cloud computing and this platform in particular, so Earth Engine, to take advantage of these huge data sets, global data sets, to look into specific problems, specific events at the local level, even if you don't have the resources to set up a very robust infrastructure at your location, or if you don't have resources to pay for commercial cloud computing services. Because in this case, if you're doing research or if you're not developing a commercial service, you can use Earth Engine for free. So this concludes my presentation, and I can answer a few questions, a couple of questions maybe, before we wrap up the workshop for today. So one of the questions we have is if we can save rainfall raster data into your device. Yes, you can. So you can use the export function that's available on Earth Engine, and you can directly export the data you're generating to a Google Drive folder. And then you can download it from the Google Drive folder to your device, and even use, for instance, QGIS to analyze the data. So yes, you can definitely do that, and it's very easy. And I think so. We have another question, and this will be the final question. If there are any label land cover data sets in Google Earth Engine, and the answer is also yes. You have, for instance, the Google's dynamic world data sets, a new data set they're making available, and it's a very interesting product. You also have access to some of the MODI's global land cover products. I think some of the USGS products are also available for Earth Engine. And then you have the community catalog. In the community catalog, it greatly expands what's available. And all you need is to call the data sets that were made available by an organization or a user, and you can definitely find land cover products there as well. So thank you so much. Again, there will be a more extensive tutorial on this. We're going to share the code, make it available, and again, we'll be in contact with you. If you signed up for the working group, you'll definitely be contacted about it. There are exciting opportunities coming ahead. Thank you so much for everyone who joined, and for everyone who stayed in the workshop until now. We are about to wrap up. Thank you so much to all the everyone in the UT Austin Portugal team, and all the IT staff who helped us to have a smooth workshop. Thank you to all the speakers, and of course to all the participants who took the time to join us. So thank you so much, and this concludes the workshop.